In this video, we're going to cover how to perform sums and products on functions. This will be a short and sweet one. We'll start by introducing the topic, and then we'll have a look at all the ways in which these concepts are tested in your exams. Let's get into it. So, what do we mean exactly by the sum or product of functions? Well, just like how we can find the sum or product of two individual numbers, we can also find the sum or product of two individual functions. The rules are exactly the same as what you're used to in algebra. Suppose you have two functions f of x and g of x. If you want to find the sum of f of x and g of x, you just add them together. The same as if you were to find the subtraction or the multiplication. The division gets a little bit weird because you have to worry about divide by zero errors, but it can be done. In fact, a tan graph is a perfect example of what a division of functions looks like. Notice how we have these vertical asymptotes? This is because tan x is actually the ratio sin x divided by cos x. The vertical asymptotes appear because the denominator cos x can go to zero. Okay, so we can perform arithmetic on functions. What's the big deal? The main thing to consider is that each function has its own unique domain. Whenever we perform arithmetic on two functions, the result is yet another function. But this sum or product of functions is only going to be valid where those domains intersect. In this example here, f of x is defined for all real numbers, but g of x is only defined for all positive x values. So when you perform arithmetic on these two functions, whether you add, subtract, divide, multiply, the resulting domain will be the intersection of those two domains, hence it would be all positive numbers. This concept was tested in the 2021 Tech Active exam. Here we have two square root functions, both defined over their maximal domain. We are asked to find the domain after adding these two functions together. From earlier, we know that the resulting domain will be the intersection of the two individual domains. So a good place to start would be to find these original domains. Square root functions are only defined where their input is greater than or equal to 0. So in order to find the maximal domain of these functions, we need to set their input greater than or equal to 0 as follows. Starting with root x plus 2, we know that the maximal domain of this function will be where x plus 2 is greater than or equal to 0. And solving that inequality gives us the resulting domain x is from negative 2 all the way up to infinity. Make sure you get the brackets right here. Since we're including negative 2, the bracket must be a square bracket. But in the case of infinity, it's a bit of a special case. Infinity isn't really a number, and you can't exactly include it in the interval. So it always has a rounded bracket instead of a square bracket. We can do the exact same thing for root 1 minus 2x. And when we do, we find that the resulting domain is from negative infinity up to a half. Again, be mindful of the brackets. Now that we have both of the required domains, all we have to do is find the intersection. The easiest way to do this is to plot both domains on a number line and then just visually observe where that intersection is. And when you do, you find that our answer is going to be D. So what's going on here? The domain of a function is the set of all possible inputs to that function. In the case of a square root function, its domain is going to be limited because the square root of a negative number is not a real result. So when you combine two functions together with different domains, here's what happens. Using our example from earlier, we know that h of x is just the sum of f of x and g of x. Let's suppose we want to find h of 0. So we go through both functions and sub in 0 everywhere that we see x, and our result is going to be root 2 plus 1. Fairly straightforward. But what happens when we try to find h of 1? Well, we go through and sub in 1 into f of x and g of x. F of x becomes root 3, but g of x becomes root negative 1, which as far as math methods is concerned, is undefined. Hence, h of x as a whole must be undefined. Sums and products actually offer us another advantage, and it has to do with how we plot functions. Suppose that we want to plot the sum of the following functions. We know the graph of each individual function, but not when they're added together. It turns out that this is actually enough information for us to get a rough idea of what this function might look like. Start by drawing both graphs on the same axes. Then break that axis up into individual vertical lines. What we're going to do is add each function along these vertical lines. The sum of both functions is the value of f plus g at that point. If you're only doing this to get a feel for what the graph looks like, then you can just eyeball it by looking at the grid. For example, along the line x equals 0.5, we can see that the logarithm is roughly negative 0.7, and the quadratic is going to be a quarter, so the result is going to be negative 0.45. If you do this for all the other points along the function, all you have to do then is draw a smooth curve connecting all of those points. And there you have it, the graph of f plus g of x. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.